part of the line. Once we get to this point, this one, we're limited by the amount of enzymes, right? That's why each one of these has a slightly different slope, because we're having more and more enzyme available. But as you're going along, time is moving along here. This one, which has 2% enzyme in it, those enzymes are so much of it, and it's working so fast, it's breaking down so much amylose so quickly, that at this point right here, it's running out of amylose. Now enzyme molecules are sitting there and they're like, they catalyze the reaction, now they have to wait. There's a lag time between contact with amylose. So at this point, the reaction rate becomes limited not by enzyme concentration, partially, but what else is limiting the enzyme rate? Or limiting the reaction rate? What else is limiting it at this point? Substrate concentration, right? So if in this experiment we're comparing the effect of enzyme concentration on reaction rate, are we interested in this part of the curve? No. So we're not going to even consider it when we standardize. We're going to say that is our final percent T at 40. This is the initial percent T at 20. So 40 minus 20. And how long did this run? 1 minute. So we're going to divide that by 1 minute. So 40 minus 20 is 20 divided by 1 is 20% T per minute. We want to get all of them in a percent T, how much starch iodine cleared per minute. So here's another one right here. This one, this curve in beaker C, that goes to 42. Goes to 40% T. And it started at 20, more or less, right? We'll just pretend. But this time it was over how many minutes? 5. So again, it's 40 minus 40% T, our final, minus 20% T, our initial, gives us 20. 40 minus 20 is 20. But it ran over 5 minutes. 20 divided by 5, 4% T per minute. So here's a 4% T per minute slope. Here's a 20% T per minute slope. It's the slopes we're comparing. That's the reaction rate. The slope's the reaction rate. So we want to get them in the same units. It's percent clearing per minute, and just for the part of the curve that is limited by enzyme concentration. Okay?
So will be just 1 onto 1?
You're going to compare. See how we're in the same units now? It's percent T per minute. This is percent T per minute. Right? So hopefully what you ended up with is, on the next page, you have a graph here, and it's percent, what are the axes? It's percent amylase, and it's percent T per minute, right? And so you should have ended up with something like this. Now your dots probably aren't on exactly that line, right? But you should have ended up with this relationship where our reaction rate increases with increasing amylase concentration. Right? 0% amylase, 2%. We should have seen something like this. More concentrated amylase ends up with a higher reaction rate. Right? So hopefully you saw a relationship something like that in figure 2. Yes?
Will we need to know how to do the math?
Yes. Yes. I will just give you this. I will graph some real data for you. And you have to use that data to calculate and pick the right reaction rate to go with the question. So for example, I would say in beaker F, which of the following is the correct reaction rate for the enzyme limited part of the curve? And then I would list, 4% T, 20% T, and I'd probably have the trick answer in there, where I'm going to use this as the final percent T for this one. Well, none of this was enzyme limited. That was substrate limited. So if you pick 60 minus 20, 40, right, divided by 5, no, that's not how we're going to get there, okay? So be able to calculate these. Apply that formula to figure out what the reaction rate is for the enzyme limited part of the reaction. Okay, well, Those of you that are not confused are welcome to finish cleaning your glassware, put it back. Last person spray off the table. Anybody that still wants help, come up here.